as a last exercise on capillarity, I'm going to look what happens with capillarity on a nanoscale, because that's actually quite interesting. Now imagine you have a capillary channel, hydrophilic, very tiny one. We have a radius here R of only 100 nanometer. And I managed to get a little water droplet in here, something like this, with a small cos theta. And now I know that the surface, the liquid gas energy of water is typically in the magnitude order of 0.05, that is joule per square meter. And I know for if this is an oxidized surface, I can say that my cosinus theta, typically 0.8, so a small number, so it's close to 1. And of course I know that my pressure here, the P atmosphere, equals 1 bar, yeah, it's atmosphere, or that equals 100,000 Pascal. That is the absolute pressure of the air pressure in the surrounding, okay? And now I know I have a curved radius here, and now I can calculate what is my delta P. And my question to you in the quiz is, if I calculate you can calculate now, what is the liquid pressure in the liquid? And the question is the pressure in the liquid, is it larger than 0? Or pressure in the liquid is exactly 0? Or the pressure in the liquid is below 0? Right, let's do a calculation. We know that delta P equals 2 gamma over R times cosinus theta. And if you calculate that correctly, I think it was 8 bar equals 8 times 10 to the power 5 Pascal. And I know that the atmosphere, the pressure here is larger than here. So I know that my liquid pressure, PL, equals 1 bar minus delta P equals minus 7 bar. Minus 7 bar. Absolute pressure. How can this be? Imagine the room I'm standing, 1 atmosphere. If I remove all the air molecules, I make this a vacuum. Of course I'll die, but if I anyway do that, I'll have exactly 0 bar. Yeah, then it's vacuum. And here I calculate I have a negative pressure. So how is this possible? A negative pressure. Does that make sense? Well, the first thing we can ask, imagine I have my cup and I fill it with water and I put it on the table. And now I suck this room vacuum. What will happen if I lower the pressure on top of a water surface? It starts boiling. Yeah? And it will start boiling until everything is boiled away. So you may think that happens here also. But in fact, that is not what happens. So people have actually tried that. And they have actually measured the pressure here. And they have actually measured, yes, it is minus 7 bar pressure in the liquid. So to understand what that actually means, negative pressure, we know what negative pressure is. And because we encounter it in our everywhere around us. So for example, let me take this pen. Yeah. If I hold this pen and now I'm going to pull the pen, like on both sides I put a force. Of course it opens, but if I pull a force, I can consider what is the pressure inside the pen. You know, right now there's no force. The pressure is atmospheric pressure because the atmospheric pressure presses together. If I do like this, I create a tensile stress inside the pen, and it's actually a negative pressure that I create. Yeah, and it's the same with the water here. I can pull the molecules away, and the intermolecular forces. You know, I just move the equilibrium position of the molecules a little bit further than they used to, so they're gonna attract each other and, you know, to keep together. So I can pull this, and the molecules will be slightly out of equilibrium, but I will see that I will get a negative stress pressure here, and it is the intermolecular forces between the liquid molecules that keep the liquid still together. You don't have that in a gas. In a gas, there is no intermolecular forces, or very, very little intermolecular forces between gas molecules. So if I make the pressure, make a vacuum, basically, you know, that's when I remove all the pneumatic pressure, and I have no energy left in the gas in that case. But here, even if I go pneumatically to negative pressure, I still have energy left in my system, and that energy is in the intermolecular bonds between the molecules. So indeed, it is possible to put liquid under strain, just like you can do with a rope or with a bar. If you just pull, you put that under strain, and you create a negative pressure inside. So normally that you would think, okay, if I do that, it starts boiling. And you would expect the same thing, that this starts boiling. However, it turns out that to start boiling a liquid, I need to create a gas bubble. You know, imagine that I have a boiling point. That means I need to create a gas bubble here in the liquid. And I can calculate to create such a small gas bubble with such a small radius that the surface energy, if you know, there will be a huge surface energy needed to create that kind of radius. And it turns out that that energy is simply not available typically. So the liquid cannot start boiling. So for liquid to boil, for example, if I take a beaker of water, for it to boil by heating it up or releasing the pressure, actually I can heat up water above 100 degrees without boiling. I call that superheating, because I need to create this first small bubble that then can grow and start then violet boiling. Yeah? And this is the same here. So this is actually supercritically heated liquid, yeah? Because I cannot generate this small air bubble that then suddenly allows the boiling of the liquid, because my system is too small. But this was just as an exotic principle, just to give an example of what capillary forces can do.